Hi, today we're going to look at probabilistic models. So I'm going to talk about probabilistic clustering, then graphical representations of probabilistic models, and also I'm going to talk about hidden Markov models and Markov processes. So this will be a superficial overview of different techniques and different algorithms, all based on probabilities. I'm going to show you quite a lot of equations, but I'm not going to go into much detail on the equations themselves. This is mostly to transmit the idea of what's behind these algorithms. And also we'll see a recurring theme here, which is that the expectation maximization approach that we saw briefly, somewhat simplified in k-means, and we're going to look at that in a bit more detail now. I'm also going to talk a bit about the next tutorials and the next week lectures for next week. So let's start with probabilistic models. Suppose that we have some model for the joint distribution of some features x and something that we can observe y. So basically this would be the joint distribution of, say, features and labels or something like that. This would allow us not only to cluster or classify examples according to features, but also it would allow us to generate examples from that distribution. So we saw this previously on generative models. When we have a joint probability distribution, we can go both ways, both in, for example, classification or clustering or generation. Now, one problem that appears in unsupervised learning is generally that we don't have these labels. So this is something that we do not observe directly on the data. There is some aspect here that we would need to know, but we are not observing. But rather it is our model that has to provide these as some hidden variables, so variables that represent something that is not directly observable. So basically, as we saw, we can solve this problem with expectation maximization. So we have some observed data, for example, the positions of our points. We have some missing data, these hidden variables or latent variables. For example, those that specify to which cluster each point belongs to. And we also have some parameters for our model. And now we want to optimize these parameters, so adjust these parameters by maximizing a likelihood function that depends both on what we can observe and on the latent variables that we cannot observe but we must fill in somehow. So this is what we solved with expectation maximization. We saw this idea approximately in k-means, so a simplified version of this. And we're going to see this in a bit more detail now with Gaussian mixtures. So suppose that our clusters represent Gaussian distributions from which the points can originate. If we have a Gaussian distribution in just one dimension, this is the formula for each normal distribution. So normal or Gaussian are synonyms, and this depends on the average, on the mean, and on the standard deviation of the distribution. So the mean will determine if it's more to one side or the other. The standard deviation will determine if it's sharper or more spread out. Now we can take different Gaussian curves and bring them together, mix them together in different proportions to represent a mixture and to create some more complex distribution. So this would be the idea of Gaussian mixture models, will be to create a more complex distribution by adding with fractional weights different Gaussian distributions. So if we extend this into n dimensions, so not one dimension but several dimensions, then the expression for the Gaussian distribution is a bit more complex, because instead of this standard deviation that we have here, which is just a scalar value, we need this covariance matrix, because the Gaussian distribution may have different dispersions in different directions. So we need a matrix to specify if it's the actual shape of this Gaussian distribution. And so the equation is a bit more complicated, but we're not going to worry too much about that. It's basically the idea is the same. It's a similar expression. It's just extended to n dimensions. And now if we have a model that includes k Gaussians, so we have a number of Gaussians, the probability of a point appearing somewhere is the result of adding the different distributions, each one with its own weight, chosen so that the sum of all the weights adds up to 1. So basically, with probabilities, we need the integral of everything to be 1, so the point being anywhere has a probability of 1. But we are dividing this in different Gaussian curves. So we add a fraction for each Gaussian curve in a way that the fractions add up to 1. So this is the idea of using a Gaussian mixture model. We have a mixture of Gaussian curves from which points can originate. This is the probability of a point originating from Gaussian curve K. And the sum of the contributions of the different curves adds up to 1. So let's consider this latent variable, z, which is something that we cannot observe when we are trying to cluster our points, which tells us from which Gaussian curve each point came. So given some point x, the corresponding latent variable z has a distribution such that adding all the possible values of z adding all the zk's gives us 1, and each one is either 0 or 1. So basically we can imagine this variable that has a value 1 for the particular Gaussian from which point x came, and values of 0 for all the rest. So this would be similar to the assignment to a cluster in k-means. In this case, we are assigning to a Gaussian distribution. And now we can define this joint probability distribution of the point and the membership to each Gaussian. We can just decompose this into the marginal probability of belonging to any Gaussian, and then the conditional probability of the point being where it is if it comes from that particular Gaussian curve. So this is just, we can write this equivalence for the joint probability distribution. Now, this marginal probability of the point coming from any particular Gaussian is simply the proportion of that Gaussian curve in the mixture. So if a Gaussian curve has 50% of the mixture, then half of the points will come from that particular distribution. The conditional probability of the point being where it is, if it comes from some particular distribution k, is given by the parameters of that distribution k, because we have this Gaussian. So if we go back here to one dimension, a point, if you know that a point comes from the green curve, then the probability of being anywhere in this axis is given by the green curve with those parameters. So this is the conditional probability of the point x having its features if it comes from this specific Gaussian curve. We just use the parameters for that Gaussian. Okay, so this basically tells us the probability of x is basically the sum of the contributions of all the different Gaussian curves. But now we can relate this explicitly to these hidden variables that tell us the probability of the point coming from each particular Gaussian curve. Okay, so now I'm going to pass quickly through these equations, but just to get an idea. So we can, if we know where the point is, we can estimate the probability of the point coming from distribution k if we consider the contribution of that distribution relative to all the contributions of all the normal distributions in that particular point. So, for example, if we have a point over here, let's say at -2, we can consider the probability of being in green as being this fraction when considering both the green, the blue, the red, and the yellow all at this particular point. So this tells us how likely it is the point to be coming from the green curve. And this is basically what we're doing here. We're seeing the proportion of this particular distribution k giving us a point at this location relative to what all the contributions of all the distributions that we have in the mixture. So this can tell us the probability of the point being coming from distribution k if we know the point, and this we know because we can observe the features, and if we know the parameters for all the distributions. So this, we'll see, is a bit of a problem because at the start we don't know what are the parameters for the distributions. But if we did know, we could compute the probability of the point coming from some distribution. And since we want to maximize the likelihood of our parameters, we want to maximize the probability of the points that we are observing given the parameters for all the mixture of Gaussians that we have. So basically, we want to find the maximum of this expression. We want to compute this where the derivative is 0, and this is the solution for that. So the mean point of each Gaussian distribution will take into account all the points and their membership or the probability of coming from that distribution. And we can do the same to compute the covariance matrix, taking into account the probability of the points belonging to that particular distribution and the distance they are, or the difference between the points and the mean of the distribution. So basically, the problem that we have here is that if we can compute the probability of the points coming from each distribution, then we can maximize this expression and optimize the parameters for all the distributions. However, we can only compute the probability of a point coming from a distribution if we know the parameters of all the distributions. And this is basically the same problem that we have in general in clustering, like we saw in k-means, which is we need the hidden variables in order to compute the best clusters, but we don't have those hidden variables, and we can only derive them from the parameters of the clusters that we are forming. So basically, we do expectation maximization here. We start with an initial guess for the parameters of each individual Gaussian in our mixture and for the coefficients of the Gaussians in the mixture. We use that to compute the probability of each point belonging to each particular Gaussian curve, and then we plug that into the likelihood function that we want to maximize, and we recompute the probabilities of the Gaussian curves. So we do this iteratively, and this is the expectation maximization approach. So to give an illustration, imagine that we are working in 2 dimensions. We have these clouds of points here, these 3 clouds of points, and we have 2 Gaussian curves. So these circles represent the 2 Gaussians that are mixed here. So one has more weight than the other, and they have different variances. In this case, the covariance matrix is symmetrical, so the dispersion is the same in all the directions. But we start with some initial value. We give one pass on the expectation maximization. We get here, we do another pass, and then eventually this converges and it doesn't change anymore. So in this case, after a few steps, we have these 2 Gaussians represented here, one that is larger and broader, one that is tighter here, and they clustered our points. Of course, using only 2 Gaussians, in this case, in the mixture, is not very good because clearly we have 3 clouds of points. So for these data, it would be better to use 3 Gaussian components, but again, we do the same thing. We repeat these steps of expectation and maximization until we have convergence, and we find the parameters for the Gaussian curves and their different contributions, which will depend on the number of points in each cloud for the complete mixture. And one advantage of this is that now we have a probabilistic model that has these joint probabilities of a point belonging to a particular Gaussian curve, and we could use these Gaussian curves to generate new points with the same distribution as we have here. So this kind of clustering using Gaussian mixture models not only can be used to cluster the points that we have, but after we do the clustering, we can use those probability distributions to generate new points with the same kind of distribution. If you want to use Gaussian mixtures in scikit-learn, you have this class, Gaussian mixture. You just specify how many Gaussian curves you want. You can specify some constraints on the covariance, because the more you constrain the covariance, the fewer parameters you have. For example, if the covariance is spherical, it means that it has the same dispersion in all directions. Then you only need to specify how large it is. But if it's arbitrary in any direction, it can be different from other directions, then you have lots of different parameters in the matrix. This is the maximum number of iterations and so on, and then you have the weights of the different distributions, the covariance matrix, the central points of the different Gaussians, and so forth. So this is easy to use. Just use fit and you can create the Gaussian curves like that. So generalizing a bit more this representation of probabilities, we can do that graphically to represent how our different variables are related. So I'm going to talk about two different ways of representing Bayesian networks. I think you covered this briefly in AI probably last year, and Markov random fields, which are two ways of representing graphically probabilities and the relationship between random variables. Then we're going to look at dynamic Bayesian networks, which are basically Bayesian networks but representing evolution over time, and then we'll move on to the Markov models and Markov hidden Markov models. So let's start with this simple example for Bayesian networks. If we have three random variables, A, B, and C, we can decompose the joint probability distribution of the three variables in the product of conditional probabilities. For example, C conditioned on A and B, and then B dependent on A, conditioned on A, and then finally the marginal probability distribution of A. So this product will be the equivalent of the joint probability distribution. If we want to represent this graphically, we can say that C is dependent on A and B. So this conditional probability here, that C depends on the joint probability distribution of A and B, can be represented by these two arrows saying that C has these two parents, A and B. B only depends on A, so B has one parent, which is A, and A has no dependency, so it does not depend on anyone. Here there are no arrows pointing to A. Of course, we could decompose this, we could factorize the joint probability distribution of A, B, and C in different ways. We can make, for example, A dependent on B and C. We can make C dependent on A and B, whatever we want. These are all equivalent in the sense of modeling the joint probability distribution in general for three variables. However, in Bayesian networks, we can take advantage of this to express some, for example, causal relations. For example, this is a classical example for Bayesian networks. The grass can be wet if it rained, because rain causes the grass to be wet. So the probability of the grass being wet depends on whether or not it rained. And it also depends on whether or not someone turned on the sprinklers to water the grass. So basically we could say that we could model this using making the probability distribution of the grass conditioned on rain and turning on the sprinklers, and then multiplying that, for example, by the probability of the sprinklers being turned on, conditioned on having rained, because if it rained, we will not use water to water the grass. So turning on the sprinklers or not will probably depend on whether or not it rained. And then rain does not depend on anything in these other variables. So this is one variable for which the probability distribution will be just the marginal distribution. So these Bayesian networks can be used to represent what causes what and what variables are dependent on what other variables. So basically what you need is when you have this graph representing the different variables, each node represents a random variable. The arcs represent conditional dependency, so this means that C is conditionally dependent on B, and in this case also on A. And then you have the parents, so you can identify all the parents of one node, for example in this case A and B, and the child node will be conditionally dependent on the joint distribution of all the parents. If some of these variables are observed, we can indicate that by usually coloring or shading the node. We can also indicate parameters, so these special nodes are not random variables, but the variables may be conditionally dependent on the values of the parameters. So the parameters may be something that is not random, that we fix, but it may affect the probability distributions of the variables. So this is an example that you have in Bishop's book that you can see there. This Bayesian network, you can write the joint probability distribution of these 7 variables by following this rule. So basically we compute the product of the conditional probability of each variable dependent given the joint probability distribution of its parents. If a variable does not have parents, then this is just the marginal probability for that variable. For example, x1 does not have parents, so it appears here only as probability of x1. The same for x2 and x3. But then x4 has 3 parents, x1, x2, and x3. So x4 is conditioned on the joint probability distribution of x1, x2, and x3. The same thing for x5, which depends on x1 and x3, and so on. So basically, you can represent graphically how the variables depend on each other, and this can be used to represent some knowledge that we have of the dependencies between the different variables. So another representation, another kind of way of representing probabilistic models is using Markov random fields. Now these directed graphical models, we can use them very well to represent these conditional dependencies between some variables and others, but it makes it harder to find when variables become independent, conditioned on knowing some information. However, with Markov random fields, it's easier to determine this conditional independency. So basically the idea here is that we have a graph joining together with the arcs different random variables, but it's undirected. There is no direction in the arcs. And the way we define independence between the variables given some values of variables that are fixed is that all the variables that are not adjacent in the graph become independent if we fix the rest, or they become independent if we fix the values of all the variables in the path between them. So this is easier to understand in a graph. Suppose we have this Markov random field for all these variables here. And in this case, what we are saying is that if we know the values of these variables in this group C, so these two here, then everything on this side becomes independent of everything on this side. So this way we can, let's say, block the flow of information from one side to the other. Let's say one example could be if a person has, say, ashtrays at home for a cigarette ash, and the probability, this will be related to the probability of the person having cancer. But if we know whether or not the person smokes, then having ashtrays becomes irrelevant. There is no longer any information that having ashtrays can give us about cancer. So this could be an example of conditional independence. There are some things here that, if we know, make this information irrelevant for determining these variables. If we don't know these, then everything can be related, but if we know them, then we don't need to know these other values. And this is what the Markov random field is represented. Which random variables are somehow interdependent or related to each other. And so if we block all the paths from one side to the other of our graph, then we don't need that information anymore. Things become independent. One property of these Markov random fields is that we can represent or we can compute the joint probability distribution by looking only at the maximal cliques of variables in the graph. So a clique is a set of nodes that are all interconnected. They are all joined by arcs. And the maximal clique is a clique that we cannot grow by adding other examples. So let's see in this particular graph, this 6, 4 would be a maximal clique because these two are joined together, and there is no one else we can join here that is connected to both 6 and 4. So this clique cannot grow and still be a clique. For example, 5, 1 is not a maximal clique because we can add 2. 2 is connected to 5 and 1, and this would be a larger clique. So this is actually a maximal clique here, 5 to 1. Using this property of the graphs, identifying the cliques, we can write the joint probability distribution of all these variables by some function of the product of the different cliques. As long as we have this normalization constant so that this adds up to 1 for all the different possibilities, then we can always write the joint probability distribution as some function that we want of each clique, and then all of those multiplied, of each maximal clique, and all of those multiplied. So what can this be used for? Just one quick example that you can find in more detail in Bishop's book would be for denoising. So let's represent the image as a graph of variables that are hidden. So these x variables, we don't know their values, and they are connected to variables that are visible. So these y variables here are the actual pixels. We can imagine that this is very large, the size of the image, and the y's are the pixels that we can observe in this original image. They can be either light or dark. They just have two values that we can represent as -1 or 1. So this is the image that we see, and these hidden variables here would be the real image without noise. So something happened that made the image go a bit bad and have all this noise, and what we want to recover is the image here that has no noise. But we can assume that the true value of each pixel in the image without noise is related to what we are observing for that pixel, because it's that value plus some random noise, but it's also related to the neighboring pixels, because the image tends to be uniform in some areas where the value of each pixel depends on the values of the neighbors. So we can model this as a Markov random field and create this energy function. So this calling this energy is comes from the statistical thermodynamics fields, where you can relate the energy of a system to the probability. So basically, the greater the energy of the system, depending also on the temperature and so on, the lower the probability of being in that state. But this allows us to think about how we want to model the noise and the real image here and create this energy function that we want to minimize. So we have some beta parameter that we can determine that for all the pairs of x's that are connected here, they contribute this term to the energy minus their product. So this means that if they have the same sign, -1 or +1, this will be negative, and so they will lower the energy. Values of x that are equals, or pixels in the real image that are equal and neighbors, will lower the energy. The same thing between each x and its corresponding y. So if we are seeing the same pixel as in the real image, this will also lower the energy with some other weight. And also we can add some bias. So this is the tendency for the pixels to be mostly in background, because we have most of the image is yellow here, but then we have some blue lines there. And if we define this energy function here, then the probability of each configuration can be related to this energy function using this formula, e raised to minus the energy. This is basically the Boltzmann distribution from statistics. But the main point here is that we can intuitively create these relations between the variables. Now we optimize this and we get the values of x, the hidden variables, that minimize or that maximize this probability, or that minimize the energy there. And so this gives us a version of the image that has a lot less noise, and depending on the parameters that we feed here, these different weights for the different terms, we can calibrate how much noise we are reducing and how much we are changing the image there. Okay, so one big difference between, basically the big difference between Bayesian networks and Markov random fields is that in Bayesian networks we are using directed acyclical graphs to explicitly indicate conditional dependencies between pairs of variables. So this can represent some kinds of dependencies that we cannot represent in Markov random fields, because we don't have a directed graph in Markov random field. So we are not expressing which variable depends on which one. But with Markov random fields, since we have an undirected graph that can have loops, that can have cyclical dependencies, we can represent these in a way that we cannot represent with Bayesian networks. So it depends a bit on what you want to represent, and mostly Markov random fields tend to be very useful when you want to isolate things that are interdependent and would become independent of other parts of other subsets if you had information for all the paths between them, for example. So these kinds of conditional independency is easier to express in these Markov random fields. But these are just examples of graphical models. You will find them in some applications because they are very useful to represent complex relations between random variables. And one example of that would be these dynamic Bayesian networks, where you can represent processes that progress over time. So, for example, a Markov process is a random process that is such that the value or the state at each instant depends only on the previous state. And there are lots of processes that follow this rule. For example, in many board games like Monopoly and so on, the place where you are in the board depends only on the previous place, and some probability distribution. So if you are in one street in Monopoly and you throw the die, then you can go to a different street depending on the roll of the die, but this distribution depends only on the street where you are now and not on the history, on the past moves that you made. So each state is dependent on only the previous state, and we can represent this Markov process like this, where this is how X evolves over time. So the joint distribution, which is all the different states of X over time, is basically the initial probability distribution, and then the probability at each instant depending only on the one before. So we have this chain here of transitions. Okay, so extending this a bit for hidden Markov models. Hidden Markov models are used for many different applications because they combine this Markov process in these hidden variables. So you can consider that you have some hidden state that is evolving over time, and then each state has a different probability distribution of emitting something that is observed. So one example of this could be this X is what the person is thinking and the Y is what the person is saying. So usually Y depends on what the person is thinking at each particular moment. She may be changing her mind as she thinks from one instant to the other, and then she may be saying different things depending on what she's thinking at the time. But we cannot observe the thoughts, we can only observe the words the person is saying. So this would be one toy example, but we can use this in more or less abstract cases, and I'm going to give you a few more examples of applications. But the basic idea here is that we have this hidden state that has probabilities of transition from different states to others. So for example, we can go from x1 to x2 with this probability, from x2 to x1 with this probability, and so forth. And each state has probabilities of emitting the observables, these y values. So basically, to specify a hidden Markov model, we need these parameters. We need a matrix of n by n, where n is the number of states. So this matrix will tell us what is the probability of having state j at time t, depending on which state we had at time t minus 1. So the matrix will give us all the combinations for the transitions between one state in one instant and the state in the next instant. Then we need, this is usually called the A matrix for the hidden Markov model. Now we also need the matrix for these emissions of the observables. So for each state, we need the k values for the different possible observables that can be emitted. So this would be a k by n matrix that tells us if we are at state j at time t, the probability of emitting at time t symbol k. And this will give us for all the different symbols, for all the different observables. And finally, we also need the probabilities at the beginning. So when we start the Markov process, this first value here, we'll also have a probability distribution that we need to know at the beginning. Note that these parameters are not all independent, because since these are probabilities, for example, for these matrices, the sum of each row and each column must be 1, because there must be one of those values somewhere. We cannot have something outside of those values. And also for the starting state, we only have n minus 1 independent parameters, because the last one will just be 1 minus the sum of all the other, because everything must add up to 1. But basically, this is what we need to specify to have a definite hidden Markov model with all the parameters instantiated. Okay, so what can we do with this? This is used for things like processing signals, transmissions, voice recognition, voice generation, and things like that. So basically, whenever you have pattern recognition in sequences, you can use hidden Markov models to relate what you are observing to some state that describes what is happening there. For example, the states may be the actual message that is being transmitted, and the observations are the signal that you are receiving, which can have noise. And this, we also do this, for example, when we are reading. If we are reading and there is a typo, there is one character that is wrong, we can immediately fix that mentally, because we have this model about what the word should be in parallel with what we are actually observing on the text. So we can infer what the actual word is, even though there is some error in the writing. So these are some applications. For example, we can predict the next value basically by computing this belief state at time t, which is the distribution of probabilities of the hidden state at time t based on all the observations so far. So if we, for example, observe these y1, 2, and 3, we could use this to predict what is the state now. Note that we cannot observe these states, and also computing all the different combinations would be usually prohibitive, but we have this algorithm that, this forward algorithm, takes advantage of the fact that each state in the Markov process only depends on the previous state. So we can compute this recursively by knowing that the initial state depends only on the initial probability distributions, and the emission at the initial state depends on the initial state, but then the emissions on the states after the first one will depend also on the values of the previous states, so we can compute this recursively going forward on the series, the Markov process. Another thing that we can do is to try to compute the most likely sequence of hidden states given the sequence of observable states. Now, what we need for this, I'm not going to go into detail, but basically we need two matrices that have the number of steps and the number of states. So the number of states in the rows and number of steps in the columns. And now we're going to fill in these matrices in order by using one to store the probability of the most likely path to each state at each time, and also in another matrix what was the previous state in this most likely path. So since the Markov process, each state only depends on the previous one, we can build these matrices in order without having to compute all the different combinations. And with these two, we can now trace back the most likely sequence of hidden states. And what this can be used for is things like speech synthesis, speech recognition, the decoding of messages. For example, wireless internet uses this Vitterbi algorithm to infer what the actual sequence of bits is from the observed signal that often has noise. So we can use the observed sequence to figure out what is the actual sequence of states there. And it's also used a lot in bioinformatics for analyzing gene sequences, protein sequences, and so on. Now we need, there is just to point, there is a difference between these two, because this one is just to compute the belief state or the probability distribution of the states at time t based on on all the observations so far. This is different from the Vitterbi algorithm, which is to compute the most likely sequence of states based on all the things that we observed. However, they have similarities because they both use the fact that in a Markov process each state depends only on the previous one to allow this computation to be made in a sequence and not having to consider all the different combinations. So one problem that we have is that in both these examples, we assumed that we know these metrics. We know the A, B, and the pi's. That is, we know the probabilities of transitions between states. We know the probabilities of emissions for each state and each observable. And we know the distribution of probabilities for the initial state. Now, to train the model, we need to figure out these probabilities. And this is another example of expectation maximization. So I'm not going to go into much detail on the equations, but the general idea is that if since we can see the observables, we have examples of all those sequences of y values. That is what we're going to use to train. If we also knew the hidden states, then it would be easy to compute. Because if we have access to all of this, to the sequence of observables and all the hidden states, we could compute the probabilities of transitions by counting the frequencies of pairs in the transitions, and we could compute the probabilities of emissions by looking at the emissions of each symbol in each state. And if we had several examples of this, we could also compute the distribution of probabilities for the first one. So if we saw everything and if we had many examples, we could easily compute all the parameters for the hidden Markov model. The problem is that we only have the y values. We don't see the x values. So this is again this problem of having hidden variables that we don't know. So if we had the parameters for our matrices, we could solve that problem because based on these parameters, we could estimate the states of these hidden variables. So the hidden states in our model. For example, we could compute the probability of having state y at time t based on all the observations up to time t and given the parameters for the hidden Markov model. This is just the kind of computation that we saw. This forward algorithm gives us the distributions of the states given the previous observations. We can also do this backwards. That is, we can compute the probability of all the output or all the observables of our sequence at the end of the sequence, starting at some time t, if we have a hidden state y at that time t and given all the parameters. So basically, if we know the parameters or the probabilities of transition and the probabilities of emission, we can use the observables to compute to estimate, to get the expected state at each time, and also to have the probability of the observables if we have some state at each time. So basically, using this, we could write the likelihood function. We need a bit more computation here, but basically we can use these to compute the probabilities of the state at time t and also the probabilities of going from one state to the other. And this is basically what we want to fill in these matrices. So once again, we have this cyclical problem, which is if we have the parameters for all our model, so all the parameters for our model, we could compute the likelihood function that we could optimize to get the parameters. So basically, by having that function, we could now compute the best values for the transitions probabilities between the states by computing the frequencies of the transition of the states divided by all of those, and the same thing for the emissions. The problem is that we do not have these parameters. And without these parameters, we cannot compute the hidden states, and without the hidden states, we cannot compute the parameters. So this is where expectation maximization comes in. We start with some initial guess of the parameters. We use that to estimate what are the hidden states in our model. So using that initial guess, we get an estimate for all the values, both the ones we can observe and the ones that we cannot observe. And now from the set of all these values, we can find the best values for the parameters, for the A matrix and for the B matrix, which is the A matrix is the transition probabilities between states, and the B matrix is the emission of the observables from each state. So, and also the probabilities of the initial state. And this is again an example of expectation maximization, where we go back and forth between optimizing the parameters and estimating the values of the hidden variables until we reach convergence. So basically, we're going to compute the probabilities of the hidden states and the emissions at each particular point, and then the probability of future emissions from any particular point. So this allows us to write the likelihood function by computing these additional probabilities from the first ones. And then once we have this likelihood function computed from the expectation of the hidden variables given an initial set of parameters, we can now use this likelihood function to find the new parameter values that maximize the likelihood. And now we do this over and over again. There is no guarantee that we're going to find the global optimum. We can get stuck somewhere. There's also a problem of overfitting. Note that we can have lots of parameters here, so we may need a large number of examples to prevent, to try to avoid overfitting. So this, there is a problem with that. But this is one way of training the hidden Markov model. Now, these hidden Markov models can be used to generate hidden states, or to generate everything, because since we have the probabilities for the initial state, the transitions, and the emissions, we can just run simulations with those probabilities and generate new sequences of hidden states and of observables. And we can also use them to classify, because given a set of observables, for example, a sequence, a string of text, a voice file with speech or something like that, we can find compute the probability that this came from a particular hidden Markov model. So if we have different hidden Markov models for families of sequences, for kinds of words or expressions or things like that, we can try to find which one matches best with the sequence of observables that we have. So basically, we can use them both ways, as generative models and as classifiers, or to group things together that are similar. They are very used in bioinformatics, for example, for creating groups of sequences of genes and proteins. Okay, so this basically is the end of the subject matter that you need to know for the tests and exams. The next lecture today will just be a preview of deep learning. We'll be having a course on that next semester. I'm just going to talk a bit about what deep learning is and some examples. And today there will still be the tutorial for P1, because there were holidays on Tuesdays and P1 is a bit late relative to the other classes. This week, officially, there are no more tutorials, but on Thursday, the 17th, I will be available at this time, so between 11 and 1600 on P5 and P6, and also on the general chat for the course. So if you have questions, I can answer them in the chat, and if you have something more tricky, we can use Google Meet and talk a bit. So during this week, I'll be available on Thursday for any last-minute questions that you have. Next week, on Tuesday, there will be no streamed lecture. There is no more matter to cover in this course, but I will be available on the Zoom meeting if you have questions, mostly for the test. Of course, this may be a bit too early for the test, because the test will only be in January. So if you need another session even if it's during the holidays, just talk with each other, see some dates that you think would be better for you, and send me an email. And if you need, I can create another Zoom meeting sometime during the holidays, maybe in the weekend before the test or something like that, if you want to have additional questions. Okay. The grades for the first assignment are nearly ready, so I only have a few more to grades, and I will be able to publish them tomorrow. So to sum up this part, we saw these probabilistic models, clustering, graphical models for probabilities, and also hidden Markov models. And in all of these cases, we saw examples or in the clustering and the hidden Markov models, we saw examples of this approach of expectation maximization. This is an important idea because in unsupervised learning, we are usually dealing with these hidden variables that we need in order to optimize the parameters, but then we also need the parameters to estimate the hidden variables. So this back and forth, starting with an initial guess and then iterating to convergence, is a very common approach on this type of problems, and it's important that you understand it and have an idea of its applications. So if you want to read more on this, you have these sections on Bishop. It goes into quite a bit of detail. The level of detail that you need to know for the test is basically what I covered here in the slides. You don't need to memorize the equations or learn them in detail, but you should have an idea of these subjects. So let's take 10 minutes approximately. We'll continue at 5 minutes past 5. See you soon.